So, hi everyone. Let's continue with our course. So, today's topic is fundamental principles of quantum mechanics. So, let's see a little overview of what we are going to discuss. So, at first, I will need to introduce eigenvalues and eigenvector. That is basically some concept in linear algebra, and it's going to be quite important for us in this day. After that, we will see matrix diagonalization, that is very related to this eigenvalues and eigenvector thing. After that, we will go to a Stern-Gerlach experiment, which is the way we are going to be introducing quantum mechanics properties. After that, we will see some the postulates, or some postulates for quantum mechanics. After seeing the postulate, we will try to understand the experiments. That would be everything. So let's go straight into eigenvalues and eigenvectors. So basically, eigenvalues are just numbers, let's say complex number or real numbers. They just a number. So, but they are special numbers that are related to a corresponding eigenvector. And here I have the definition. You can read it if you want, but the idea is quite simple. So basically, you have a linear operator acting on a certain vector of your Hilbert space. So that vector is going to be an eigenvector of this linear operator if when the linear operator is acting on the vector, it gives you the same vector but multiplied by a certain number. So this would be the eigenvector, and this will be the eigenvalue, right? So that's the idea of eigenvectors. So the point here is that it depends on the properties of the operator, but when working in quantum mechanics, the operators are going to satisfy these properties we need. So it will be really important to obtain the eigenvectors and eigenvalues of any operator. Mm. So I believe that would be clear enough. So that's the meaning that you have any linear operator acting on a vector, a special vector. So, and if you get the same vector but multiplied by a certain number, that would be your eigenvector, and this number will be the eigenvalue, right? So how do we obtain? I don't know why there is here this. Sorry about that. How do we obtain these eigenvalues and eigenvectors? The procedure we follow is called matrix diagonalization, and this is for I mean, we can use this when we can do to use the matrix representation for the linear operator, because if you don't have a matrix representation, you cannot follow this procedure in order to get the eigenvalues you want. So just uh, take this equation, and this equation is exactly this one, right? So if you, let's say, take this into the other side of the equation, you get this other equation. I mean, and here you have the identity matrix, since this is like a matrix equation. So you need, since this is just a number, you need to add the identity matrix here. So this is just moving the stuff from the other way to this one in order be to do the calculation, right? So this is the equation we must follow in order to get the eigenvalues and eigenvectors of any linear operator A. So here I write down three really important matrices that are known as Pauli matrices. There is a lot going on I mean, in the sense that these matrices you can obtain them from doing some special calculations, I would say, but that's something that we are not going to do. But basically, these matrices are very important in quantum mechanics because uh, they represent certain physical systems, like certain observables, as we are going to define and see uh, later. So these are going to be important matrices. Something interesting to or quite important to say that they are all in this case they are all written in the same basis, right? Because remember that for writing things in matrix representation, you need to have a basis. Mhm. So, for example, I mean, this is a bidimensional system since we have s two-dimensional square matrices. So the base is going to be two vectors. And I can call, I mean, the vectors can be different things. I can call the vector 0 and 1. I can call the vector A and B and W, right? I mean, the names are names. But for these people here, also we will understand this a little better in a few moments. I will just call the first vector. I am going to call it the up state, state, right? And then let's write here theta set, sorry, and the down state set, right? Let's just call the basis in this way. Why am I calling this in this way? Well, we will see. We will see. But I mean, this is just the same as calling 0 and 1. I mean, I could have done that, and we will do that in next week. But just remember that these are just names for representing certain vectors, and the vector can represent a lot of different abstract things, right? So let's do that. So an important mark here is, for example, this matrix, do you see, is different from the rest for sure. But the interesting thing is that it is a diagonal matrix. And why this is interesting? Because when you have a matrix in this form, that means that the basis you are using is an basis made out of the eigenvectors of this operator. Let me explain myself a little better since uh, so you have so this vector will be in this basis, right? Will be the 1 0 matrix column, and this other vector. Well, let's write. Sorry, let's write in color black. 1 0, also up. This will be the 0 1 vector, right? Because in this basis here and using so that will be this is the very same, and as we have done a lot of time before. So if I apply sigma theta to, sorry, I have done exactly the contrary, right? Sorry for that. Yeah. So just write the matrix for example. So apply this, and you will get exactly this. If you do the matrix multiplication, I believe it's quite straightforward. So this is just the same vector, right? So this vector, uh, let's say this vector is an a vector of sigma theta with eigenvalue lambda mass equal 1 uh, equals 1. Yeah, because if we apply the operator to our vector, we get the very same vector multiplied by 1, right? In this case, it's quite simple because we are just multiplying by 1. If you do the same for the down vector, you will basically get this here. So in this case, the eigenvalue is -1, right? So whatever every time you have a matrix in your diagonal form, right? And that's means the only terms that are non-zero are the ones in the diagonal of the matrix. It means that you are writing that operator in the basis that is made out of the corresponding eigenvectors of the matrix. So, that's mean of your operator. But for example, we could want to maybe find out the eigenvectors of this matrix, right? And this is not that easy because this matrix is not diagonal, right? I mean, it's exactly the same as the diagonal. So in order to find the eigenvectors of this matrix, we have to follow this equation here, right? So let's do that. All right, this will be a quite easy example to find the eigenvector of the matrix. So let's go, right? So we have our sigma x matrix, right? 0, 1, 1, 0. Very well. So what do we do? So we are going to use this formula since we have our operator is sigma x. We are going to use it lambda minus e and the vector. Uh, right? This is the equation. So in order for this to make sense, there are two things. There is a thing that must be satisfied, and this is that the determinant of this expression must be equal to zero. I mean, at the end, this is a matrix, right? Because this is just, in fact, this is just this matrix. One, right? Yes. This is just this matrix because we have our operator sigma x with the ones here, and we are subtracting the eigenvalue which we don't know yet. I mean, our purpose is to find out the eigenvalue. So we have the eigenvalue here multiplied by the identity matrix, and the identity matrix is just the identity matrix is this one. I mean, just the identity. So that's why we get this. So one thing that must be satisfied is that the determinant. I mean, let's go here. This must be zero in order because at the end we are like solving uh, a system of linear equations. So in order to find more than just one solution, we need this to be satisfied. So that's the first step. In order to calculate the eigenvectors and eigenvalues, the first step is to do this calculation. And with this calculation, we are going to be able to find out the eigenvalues. So in this case, it's quite easy, right? Because if you, I mean, I hope you are familiar. I mean, the determinant of a matrix is just, in this case, would be, I mean, if you calculate the determinant of this matrix here, and the determinant is denoted by this bars, right? This will just be this guy square minus 1 square, right? And this will just be this minus 1 square, sure, equals to 0, right? So this is our equation. So now I believe that this is quite easy to see that the eigenvalues is just 1 or minus 1. We get the same eigenvalues as the eigenvalues that we have here, right? Minus 1, if you want, plus 1 and minus 1, right? We get the same eigenvalues. This is something that has to be to the, let's say, physical properties. I mean, this is pure mathematical stuff, but these matrices, if you know where they come from and the physical meaning they have, we will discuss this just a little because it's a little complicated for this course. But it's logical that they must be the same. I'm not saying that for every matrix you normally won't have the same eigenvalues, but in this case it makes sense. So anyway, we get some eigenvalues. It doesn't have to be the same, but in this case it is. So how do we find the eigenvectors? So now we take this equation and we have to our eigenvector, which we don't know yet. We write it in this way. This is just our general linear combination. So we need to do a calculation for every, let's call this plus minus, right? For every eigenvalue. For example, uh, let's take lambda plus, right? Equal plus one, plus one. Sorry. Uh, yeah. So take this expression, right? Just this. So with lambda equals to one, it will be minus one, 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 minus one. Our vector and equals to 0. This is just uh, this equation here. If what I'm writing here. So if you go to the equation, you will find that you have two equations, but they are the same. So at the end, this leads to alpha equals beta. So, and then it means that any vector in your Hilbert space that have alpha and beta are that I mean, like when alpha and beta are the same number or same complex number or whatever, uh, you will have that vector is an eigenvector of of the sigma x operator, right? So let's just take, for example, I have called this B1, but I just going to call this the up again, since it has the eigenvalue plus one, right? But with the x here, right? Because the basis I was using what the up and down state, but with the set here, now I'm just calling, and again, this is just a way of calling the numbers, right? It's not. I mean, it has some physical meaning because I know what is behind this, but in our example, it's just a way of calling these guys in a way or another. It doesn't have much importance. So, for example, it could be this vector here. Uh, right. I mean, this is just if I write the matrix form, and you may be wondering why I choose this number, because I could have been able to choose any number from just like I could have chosen any number, right? So uh, I will explain this later, but the idea is that the important is that this vector, the norm of the vector, right, that we have discussed a little, needs to be one for quantum mechanics. We will understand this when we see the postulates. But if you calculate the norm of the vector, this will be just the square root of this square and this square, right? Square, yes. So this will be the square root of one, and this will be one. That's the only reason. So that's the vector use. And for the other vector, you will get for this eigenvalue, you can do exactly the same. Yes, and basically you will get uh, if you do the calculation, that is exactly the same. I'm just going to move forward because we need. I'm just going to call this down. So you will get something like this, something very similar, but with a minus here, right? It's quite straightforward. So we have already found the eigenvectors, right? Here we have one eigenvector, here the other one, that from for this operator. So if we wanted to, we could now rewrite every operator. I mean, this three operator, we could rewrite this in the other basis. If we call this the set basis, we could also write them in the other basis, like this basis here. I mean, I haven't really discussed some important things here, like, but the idea is that for the operators that we are normally going to use in quantum mechanics and for sure in quantum computing. When you find the agent vectors of any operator that we are going to be working with, uh, this set of eigenvectors of the corresponding operator are going to form an orthonormal basis, right? I mean, they are going to be orthogonal, and that's not so easy to see in the sense that you need to prove it, but we are not going to do that. Also, the normalization is easy. It's just multiplying by a number in order to make the norm be equals to one. But the idea is that, and this is quite important, but we are not going to prove that if you find the eigenvector of a operator or linear of a linear operator for sure, that satisfies certain properties that are going to be satisfied always in quantum mechanics, and we will later understand this. These eigenvectors are going to be able to form a basis on orthogonal basis of your Hilbert space, and for sure an orthonormal one. Very well. I hope that gives an idea of matrix organization. I mean, this is something that you need in order to properly understand. You need to practice a lot, do matrix organization in different cases in order to get experience and practice and understand things properly. And this is quite a fundamental thing. It's extremely useful in a lot of things, like for example, even in classical mechanics, you find matrices and trying to diagonalize, finding the eigenvalues and things have a lot of physical meaning. So this is like important mathematical tool idea, right? So, and for quantum mechanics is absolutely uh, fundamental. So let's go to see a little of the Esther-Gerlach experiment. So here, I know I have tried to reduce as much as I can the physical complexity, I would say, of the of the experiment, since there are a lot of details. But let's try to understand just a little bit. So in the Esther-Gerlach experiment, I will give my detail in the next slide, but we're going to be measuring a property that is called the spin of a particle. You may have heard this before or not, I don't know. Um, Having a proper understanding of the spin in order to know where does the spin truly comes from requires, I have it right in here. It requires like group theory and a little special relativity. So it's quite a complex thing. But normally, in order to take some physical sense about the spin, we usually say that the spin has to do with a ball, right? That I mean, it's not the. I mean, this is funny because you know, physics guys, when we talk about the spin, they say, okay, imagine a ball that is spinning one way or the other way, but it's not a ball and it's not spinning, right? I mean, this is quite funny to say, but it's true in the sense that for you to make a visual idea of what is the spin, you can for sure think about this, but deeply in the split, really strictly mathematical way, it's not that. I mean, it's come from different things. But let's just take this picture. So we have a particle. It's going to be spinning in one direction, right? As I have right here. So this will represent our up state in this direction, right? That I'm going to call set. Right? And now you might understand a little why I did call the previous vectors, right? On the basis, you might understand why I did call them in this way, because they are going to be, we are going to use them in this Esther-Gerlach experiment. So, and this will be the down state when the ball or the particle is spinning the other way around. So it has because all right. Another thing, like the spin is understood in some ways as an intrinsic angular momentum that the particle have, thanks to this spinning property. Let's say so if the ball is spinning in this way, the angular momentum will go up. I mean I will understand that you don't follow me exactly in this, but just let's state that as something that is like that. So if the ball is spinning this way, the angular momentum will go up, and if the ball is spinning in this way, the angular momentum will be down. So that is going to be our up and down state that are going to describe the particle, right? So that will be our Hilbert space, right? The Hilbert space will be made out of these two vectors, and each vector represents a physical state of our system. We will also discuss it a little more when we see the postulates, but that's the in order to at least understand a little of what we're going to do. I'm just saying this. So we are going to be measuring whether the particles are up or down in our system. I mean, we are going to be a specific set of atoms, and we will are going to be measuring this. How do we measure this? So in order to do this, there are like a lot of physical things and solving differential equation and stuff. I mean, it's not difficult, but it's difficult for, I mean, high school level for sure. So let's just take that using the a magnetic field, and magnetic field just, yeah, like magnets, right? Using a magnetic field, we are going to be able to change this direction. I mean, we can like control a little. So I'm just going to, without giving much more details, I'm just going to call this Stern-Gerlach device, and it will be useful to measure this up and down end state, but for in the direction, in every direction. I mean, alpha is just a unitary vector that gives us the direction, right? So I mean, for example, alpha will be this direction, right? Set. So I will be measuring the P up and down just in this direction. But I could also be measuring this property in, for example, the X direction, right? So that's that's a basic things that we need. All right. So what is the experiment about? So we are going to use. Well, we are going to. I mean, we're not going to do anything, but in the experiment they used a bin of silver atoms. Right? I mean, they have some furnace here, so they were, yeah, the furnace was from the furnace we get this beam of silver atoms, and these silver atoms are going to be passing through different sets of Stern-Gerlach devices from different angles that we can. I mean, we can set up this as we want in then measurement, do the measurement, and after that, I mean, we can try to make some conclusions about what is going on inside. So the main idea is that we have, yeah, the furnace and a bin of atom in a certain initial state. That in this case, I mean, we don't really know the initial states of this guy because they come from the furnace, and in that case, I mean, we don't know the state that they can. I mean, we may be able to use this experiment in order to know the state of the. Yeah, I will explain this later. I mean, since it is a physical furnace, like you have some stuff there, is not like perfect in a sense. It's not prepared to give you an exact state. It's not going to give you this state of this other state. So you don't really have information about the state that you are getting out of your furnace. So at the end, basically what you get if you have a mix of up and down, like a random mix, right? Some particles are up, other particles are down because you don't have control over the particles that get out of the furnace. So every time that you measure, for example, here we are measuring on the set direction, we are going to get 50% up, and the other, I mean, the half of the particle are going to be with the spin up, and the other one, the other half is going to be the spin down. Just out of this randomness that we don't know. I mean that since the furnace is not prepared to give you any concrete state, we have at the end, given probability and statistics, the most probably probable outcome is that you have 50%. I mean, half of the particles are going to be up and the other half down. Well, I think I have repeat that enough. So, right. So let's move into more interesting experiments. So for example, let's take this one. You have your silver atoms, all right? This is the very same as I have now discussed. So let's say that you take just this portion of the, like this half of your whole beam, and after that you do the same measurement. So in this case, it's quite straightforward, or maybe easy to see that at the end, all right, so if you do the same, but you will get again the same state, and you in this guy you won't find any guy with the spin down, right? That's uh, I would say expected, right? So let's do another experiment. So now we have the same here, 50%, 50%, and now we do the measurement, but using the X direction. So in this case, we get that from this half, right? Because we are taking half. I mean, if we have 100 particles, and here we have 50 particles, we are just taking these 50 particles here in order to do this measurement. So, and if we do that, we find that we have from these 50 particles, we have 25 particles that up in this up step in the X direction, and 25% that are down in the X direction also. So that's this result might be more confusing, right? Uh, I don't know what are your thoughts about this, but it will it will get worse, I believe, with the next experiments. But that's that. I mean, imagine you are a scientist. I mean, you are doing this experiment, and you find this in your when you measure, you find this, and you are like, all right. I mean, this is the result. This is what nature is telling me. Later on, you will have to try to explain this somehow, right? So let's move on to more experiments. All right. So now this is the same. This is our beginning. So let's take this 50% of our atoms in the up state, and then again the same X measurement. So we get the same. I mean, until this point, it will be the same as this whole experiment, right? We are in this place. So now let's say I want to take these guys here and do another measurement on them with the set direction. And now it's again quite surprising because we get half of these guys are going to be up and the other half is also going to be down. And this now is maybe brain, your brain may be quite, uh, I don't know, out of your mind, right? Since at this point, we did only take the up state, right? I mean, all this down where we didn't take it then. I mean, we just took this up state, and now again we face here the down state. I mean, how is this possible, right? This is it's quite. I mean, at the beginning, this must be like a nonsense, right? This is not working right or whatever. But this is how things work. So I mean, later on we will understand this for sure. Let's do one more experiment. Just from until this point, these two are the very same, but there is a difference. And in this point, we take the whole beam of atom that we have here. I mean, we take both the up and down state in the X direction. And if we do that, now we get that all these people, or all these guys, all these silver atoms are going to be in the up state of the set direction, and none of them are going to be in the down state. And that's the result of the experiment. Mm. This is also quite confusing because I mean here we were getting down state. Now we take everything and we are getting only the up state. So we are like, yeah, what's going on here? Like, how can we explain this, right? So let's go into the postulates. You know that we are. I mean, we are going to now see the postulate, and after that we will go back to the experiment and try to explain why this is happening. And that would be the end of the day. So, but let's go. So the first postulate is how do we describe the physical states of a system in quantum mechanics. I have already said that really, but basically, your physical system, every different state of your physical system can be represented at a vector of your Hilbert space, right? And it's going to be a complex Hilbert space since the field that we are going to be working is the complex number, right? And the funny thing here is, all right, if we are working with sun state, for example, now I have called here 0 and 1. It could be the up state and down state. I mean, they are just labels, names. You can find an state in your Hilbert space that is a linear combination of both 0 and 1, right? Because we have done that a lot of times. So if we, I mean, for example, like, because if this were the up state and the down state, and you have here a linear combination, let's say, I don't know, maybe, yeah, for example, this one as the same as before, uh, 0 and 1. So you may wonder now that what is the state of my system? Is 0 or is 1? If I have this state, you don't really know exactly, right? Because I mean, if your state is just 0, there is no doubt the state is 0, or is just 1, it's going to be 1. But when you have a linear combination of your physical states, what we have is what is called quantum superposition, right? This is quantum superposition, just linear combination of your states. That's, I mean, I don't know if it sounds complicated or easy, but that's the idea. So when you have a linear combination of your physical states, is your system is in quantum superposition, and that is the state that describes your quantum system, right? So this is you normally when people are talking about quantum, like people that might not know that much about quantum, they say stuff. No, in quantum you can be either in two different places at the same time, or yeah, something like that. For example, in this example, you can be either in the state 0 or 1 in the same time. I mean, and that's true in some sense, but it's not exactly the at the end when you measure. It's not exactly what happens, because it's true that the state describes a system that is in both states, like 1 and 0. But the coefficient here, this alpha and beta, are I mean, because you could have this one, you could have other vectors. For example, let's take I can write there. Yeah, let's take one half. The, I don't know. Again, this must be normalized, and that's I am thinking in order to do that. No, 1/2 0, and maybe I this will be 1/4 raised 3. Uh, I have no more space. Just, for example, it will be another possible physical vector. I hope you can see that clearly. It's a little messy here. But the idea is that you have coefficients that can be different, can be any complex number. The only condition is that the vector is normalized. That I have also read here. Yeah, that's I maybe I should have highlighted this. The vector must be normalized. Why must the vector be normalized? Why is this so important? Because as you have seen here, when you measure the vector, and that's mean you when you measure, you are going to be to it either 0 or 1. I mean, when it gets to measuring the system, you are not going to be measuring, okay, it's in both systems, no, in both states. You are going to get either 0 or 1 when performing the measurement. And we will also detail more about this in the next postulates. But the thing is that this coefficient here gives you the probability of getting one state or another when measuring. For example, the probability for this state to go to the 0 state is going to be this expression, and this is just the norm of the square of the norm of the scalar product of your state with of the state you want to know the probability from the state that you have, right? At the end, it's going to be the modulus square of this complex number, because this can be a complex number, and of if it is a real number, it will be just the absolute value square. So, and the same for this one. I mean, exactly, if you want to know the probability for your general state to go to the one state, just perform this operation, and we will be the module square of the complex number beta. So the important thing is that if you sum this, I mean, these are probabilities, right? An important thing about probabilities is that the sum of all possible outcomes must be one, right? Because it must be something in the sense that you cannot have a sum of probability that is less than one or greater than one, because something must be wrong. So it's important that I write it here. Alpha modulo alpha square plus beta square is one. And this is basically telling us that the norm of this guy must be equal to one. That's exactly the same. So normalization of the vectors in your space has to do with have a proper probability. It's just that. That's the importance of having a normalized vector, and that's why I always, and we are always going to be working with normalized vector when we talk about quantum mechanics, because the coefficient give you the probability, and all the probabilities must sum up to one, right? That's important. So this will be the first postulate. I will now let's go to the second one. So observables. I have also say something about this when discussing the experiment, but I mean, how do we define observables in quantum physics, right? Or quantum mechanics? How do we work with something? I mean, I want to measure this, or I want to measure this other thing. How do we represent observables? So an observable in a physical system is going to be represented by a self-adjoint linear operator. I mean, it's just a linear operator that is satisfies the property to be self-adjoint, right? This is just, let's say, a definition, but the important thing here, and the main reason for this, is that is if you have a self-adjoint linear operator and you try to calculate the eigenvalues of this operator, they are all going to be real numbers. I mean, they are not going to be complex numbers, right? They are going to be reals. And that's important for the next postulates that we are also going to be discussing. And also very an important thing is that if you have an operator that satisfies this, it means that you can always find an orthonormal basis out of your eigenvectors, right? This is also something that I have said before. Like if you find the eigenvectors of your linear operator, you can form a basis out of this set of eigenvectors. So if your operator satisfies this property, you will be able to do that always. And these are the operators that we are going to be using in quantum mechanics, because at the end in quantum mechanics, we are going to be working with different types of observables. Let's say spin, angular momentum, the x position, z position, or different operators, right? That are going to represent physical quantities. That's the point. So they are all going to be self-adjoint operators. Okay, that's good enough, I think. So an important thing is that since I have said that you from if you measure, you get a certain state for your system, but with a given probability, right? I mean, you don't know the outcome of your experiment, but you know the probability of each outcome, right? So in order to properly make measurement, you don't know. I mean, if you do a measurement, you don't exactly know what it's going to be. You just know, okay, it's going to be with 60% probability, it's going to be this state, and with 40% probability, it's going to be the other state. But you don't know exactly what is going to be in the next measurement. So in order to calculate values more like an average value, right? In probability and statistics is quite the same. You calculate when you have probability, you calculate the average in order to give a more like more information out of your experiment. So here we calculate the expected value, and the expected value is just defined in this way. I mean, for any operator A, any state phi, the expected value is defined in this way. It's just this bracket, right? So the expected value is just a time average, right? But you have certain probabilities, and you at the end you multiply the probability with the possible outcome. Here I have done a little calculation in order to properly understand that this is going to be the probability, right? Remember, oh my god, probability prop. This is just this, right? Remember, this is just this. In here, I mean, I think I must hurry up a little, but I just introduce remember yesterday when we were saying that if you have a basis and you sum, for example, here, this will be the identity, right? So I've introduced the identity 2 times, right? One here and the other one here. I have just done that. Um, uh, I believe that maybe you can try to understand this maybe on your own, and for sure ask me any questions since I have more things to discuss. We can see this on Discord later on, for sure. But this is just more complementary, I would say, just for you to know that the important idea is that observables are represented by self-adjoint linear operators. I didn't say this. All right. I think this was in the next slide, but when you measure, because all right, the operator is represented. I mean, the observable is represented by self-adjoint linear operator. But what are the possible outcomes of your linear operator? They are the eigenvalues, right? I mean, for example, in the spin up and down example, we were getting either up or down, right? And the eigenvalues were +1 and -1. So that was the possible outcome because that were the eigenvector of our linear operator that was representing the spin of observable. So basically, the idea is that if you have a linear operator that is representing your observable, it's going to this operator is going to be self-adjoint, since it's representing an observable, and the possible outcomes of your measurement are going to be the eigenvalues and eigenvectors. I mean, if you get the eigenvector is going to represent the physical state of your system. So that are the possible outcomes of the experiment of the measurement, right? Very well. So here. Oh, yeah. Oh my God. I have moved. Sorry about that. Yeah. The A. Yeah. So probability. This is just a general way of writing the how to calculate the probability, because we have I mean we have already seen how to calculate the probability, but this is oh my God. This is half moved. I don't know why. If a quantum system is described by a normalized vector P, the probability of obtaining the eigenvalue A sub E. I mean here it must be A of an observable represented by a linear operator can be calculated. Linear operator, a linear operator A can be calculated in this way, and this is just the probability of getting this eigenvalue if your physical system is in this state, and this is the projector that we were discussing just the other day. So if you do the calculation, remember projectors can be written in this way. So if you do this calculation here, I mean, it's quite straightforward. I mean, it's just a line in order to get to this expression. But I think well, my idea was to do that here, but since I don't have much time, I will leave that to you. Ask me any question for sure if you have any problem. But it's just introducing this in here, right? Work a little with the bracket notation using the complex number properties. You should be fine. So this is just a general way of writing the probability, and it might be good to calculate the probability in this way. sometimes. Right. And this is going to be the last postulate that we are going to see, and this is also very important. So what happens when you measure the system? When you, because you know in quantum there is quite a trouble to understand this properly. But when you measure a system, you are interacting with the system in some way, because if you weren't interacting with the system, you wouldn't be measuring, right? So you have a quantum system described as normalized state, normalized vector field, and we measure an observable, let's say represented by this operator, and you get an eigenvalue. This eigenvalue, for example, what is the final state of your system, right? So the final state of your system is going to be this state. I believe that this expression is quite ugly, or maybe it looks like very complicated, but at the end you are just projecting on the space of your eigenvector and dividing by the norm of this same vector. If you call this, I don't know, W, for example, in here you have the norm of W, right? I mean, I hope uh, is it to see? I mean, and you do this just in order to this vector to be normalized. That's why you are dividing by the norm of this vector, of this vector. And since I know this expression can look, yeah, a little complicated, and the idea is more simple than that. So let's say you have this vector is in this linear combination, and you measure A and you get A1. This means that the final state is going to be this one. So what's the important idea is that if you measure a system and you get a certain eigenvalue, the final state of the system corresponds to the state of that eigenvalue, right? Because you have this linear combination, you measure this eigenvalue, so at the end you will have the corresponding state. Since it must be normalized, at the end you have here one, right? Because the norm of this vector, well, I mean the norm you're using is properly normalized, it's going to be one. So that's something very important in quantum mechanics. That if you measure an eigenvalue, the physical state of the system after that is going to be the corresponding eigenvector. Also, a note here is that eigenvector, when talking in quantum physics, yeah, let's just say that you can say eigenvector, but it is usually also called eigenstate, because since vectors are going to represent a state of your physical system, instead of saying eigenvector, you can say eigenstate, but it's the same, right? I mean, it's just for you to know. So yeah, right. So let's move on. Right, very well. So now let's try to understand a little better the experiment we have seen before. In order to do that properly, I have just here defined a little things. Like remember this Pauli matrices that we have find the eigenvectors before in the sample we did with the matrix diagonalization. We have our sigma set uh, uh, matrix that is going to be the observer. I mean, when we were measuring the spin, at the end we were measuring these operators that are operators that represent the spin. Right? I know this is just like something I give to you in the sense that I'm not explaining why this is like this, but this is because it's more complicated. But let's just state that these Pauli matrices represent spin operators. So the sigma set is going to be for the up and down state in the set direction. So the corresponding Hilbert space, the Hilbert space is the same, but the corresponding eigenvectors are these guys. And I also have the sigma x operator that is going to be the up and down state in the x direction, let's say. So you have this is the very same Hilbert space, right? Because the space is the same, the spin space, if you want, but using a different basis, right? Because remember that you can have different bases in your Hilbert space. So a fundamental and important thing, that's the reason that the experiment looks so strange, is that these operators don't commute, right? These are operators that represent physical quantities, but they don't commute. I mean, and a cerebellum that don't commute is just basically, in this case, is just sigma x. Sigma zeta is different from sigma z, sigma x, right? That's the meaning of not commuting, because if they commute, in this case, they commute, but this is not our case for these operators. And this is something I said when discussing linear operators, that it's important that linear operators don't commute in general. And you can test this just doing the matrix multiplication. You know that matrix multiplication is not commutative, so it happens the same with the operators. This here is how we define the commutator. So if the commutator equals zero, if these guys are the same, it's going to be zero. They mean that the operators commute. But if this is different from zero, in this case it is, they don't commute. And when two operators don't commute, and they represent, for sure, when they represent physical quantities or physical observables, they are called, they are incompatible, right? Yeah, they are called incompatible, and we are going to understand this better in discussing the experiment in the next steps. But basically, the idea is that you cannot have, because you can say, okay, my system at the end have this eigenvalue is up in the z direction, or is down in the z direction, but you cannot, it cannot either be up in the z direction and down in the x direction, for example, or up. It doesn't matter up and down. The point is, it cannot have a concrete state in one direction and also in the other one. It can only be defined in one of the direction, and this has to be with the these commutator properties that the operators don't commute. I understand that what I'm saying maybe is quite a lot. I didn't say this was going to be easy. I'm trying to explain this the best I can, but this is not easy for sure. So this needs practice and reading books and do examples and exercises. So let's try to understand this a little better. So, all right, we have here the experiment one. It was quite easy. So understanding that we have this first outcome, right? Because remember here we didn't exactly know the state of the system, since it comes from a furnace and it's random, and we don't exactly know how the furnace, how are the spin in that leave the furnace. So let's start here. And if we take this here, this silver atoms, so the state of each silver atom is going to be the up theta state, right? So if we measure sigma six again, since this is an eigenvalue, no, this is an eigenvector of sigma set operator. We are, and it's not in quantum superposition. We are going just to get, at the end we get the very same, right? Yes. So this will be, phi prime. Yeah, this will be, how to say this? It will be the second step that we have here. Second, right? That was an easy one because since we're measuring the same state, we get. We have we have an eigenvector of the operator, and we get that same vector since we are measuring the corresponding linear operator of the eigenvector, right? Let's go into the same one. I repeat myself a lot, I believe, just to, since I want to make everything clear, I think I repeat things too much. Anyway, so this is more interesting. Let's start here again. We have, green, maybe, same as before. So we have here our initial state. Yeah, right. The initial state is going to be the up theta state, but now we are measuring sigma x. Right? We measure. I'm not going to write measure design, just sigma x. So what happens here? What happens here? So we get the we are going to get the eigenvectors of sigma x with certain probability. So in order to do that, to do this calculation, we need to write down this vector in the in this basis, like in the x basis. Like, let's call this the x basis. We need to write this in this basis in order to properly know the final state, since from the postulate we have discussed, we know that the outcome will be an eigenvector of this operator, right? And the eigenvector of the operator are these people here. So remember what we have seen in the matrix diagonalization at first. At the end, we calculated that this, well, we did not exactly write this, but if we invert the relationship, we can see that this identity holds, right? I mean, we can write this vector in this way. And in order to see that, you can go to the sample we did at the beginning and try to see the relationship, the relation between the vectors, because the matrix I did the diagonalization at the beginning. It's just the sigma x matrix. So I mean, I did find out these vectors, and you can go to that example and understand why this can be written in this way. Right. So if we do this, we can see that at the end there is going to be 50% probability, because if you have the probability here, the probability of sigma up this up state of going up or well, down or up, I mean, it doesn't matter, it's going to be the same, is 1/2. And this is just, I mean, 1/2, because this is going to be the modulo square of this guy, and this is just 1/2, right? Since the coefficient is the same for both states, the probability is the same. So that's why at the end, you get exactly this state, right? In here, you get exactly, because you have here 50% of total atoms. So if you measure the x direction, you have a 50% probability of getting the up and down state. So at the end, you have 25% of your total atoms in the up state and 20% of the atom in your down state. Since here you are just taking the 50% of your total atoms. I hope that is more or less clear. Let's move into this one. So until this point is the very same as we have discussed here. So let's just say that our state, yeah, well, let's take this one. So in here, one, because this whole state, right? If you want to, let's say, yeah, right one. This whole state would be the linear combination we have seen, right? I mean, that's why, well, up x and down x, right? This is the linear combination. That's why you get a half are up, half of the atoms are going to be up, and the other half is going to be down. Yeah. Let's be quick because we have the clock is running, right? So if you go to this one, we take just the up ones, right? And you get a measure theta, I mean the set direction. You have to write this in the other basis, but the vector is the same. You can check this here. Set these are just vectors, right? Very well. So at the end, again, if you measure sigma theta, there is probability, the probability of sigma of this guy to go to the up set or down set is going to be, sorry, I don't have a space, 1/2, right? And this is why, again, if you have 25%, you get the half, and the other half are going to be either up or down, because you remember again, you get this is not an eigenvector of sigma set, so you have to write this in the corresponding eigenvector basis, and you get, I mean, this is the possible outcome. So you have two states with a certain probability, and in this case, the probability is the same. And there is a 1/2 probability of being up, 1/2 probability of being down. And this is what you get this result. And lastly, just this sample very quickly. In this case, you take uh, the whole set. So at the end, you have this state right here. And again, you measure down, please, down. You measure sigma set. But remember that this state is exactly the up state, right? That we have written here as a point here, remember? This is exactly the up state. So you get the up state for everything. So we have explained all the experiments using these postulates of kind of working a little with the vectors. And that will be the end of today. So I understand that maybe at some point I've been faster than usual or not. I don't know. I hope everything is clear, more clear. In here in the reference, I have added some lecture of one of my professors that I have in my bachelor's degree. Here, I mean, they are in English, the notes. So I think they are going to be, you can use them. I mean, there is like a lot of more material and for sure more advanced in the sense that because this is material from the last course from my bachelor's degree. So this is the four year, but you can use it for sure. It's on his website and also some books here. So see everyone in the next day. That we will be starting with the quantum computing.